Resolving power. Resolving power is the ability of an optical instrument to distinguish two physically separated objects as two distinct objects. This is the diffraction pattern of this bright red point. If you have another diffraction pattern, the blue color spot, you have the blue color wave. The minimum visual angle between two objects that can be resolved by the instrument is called a limit of resolution. The reciprocal of the limit of resolution is known as resolving power. Now these are the three cases. The diffraction patterns, if they separate out like this is Rayleigh's criterion for limit of resolution or resolving power. Look at the first figure. This is the unresolved one. The separation between the central maximum of the two objects is very less than the distance between the central maximum and the first minimum of any of the two objects. The second one is just resolved. Here, the separation between the central maxima of the two objects is just equal to the distance between the central maximum and the first minimum of any two objects. And as you can see in the last figure, it is very well resolved. The two dots are well separated. In that case, the separation between the central maxima of the two objects is greater than the distance between the central maxima and the first minima of any two objects. So that's Rayleigh's criterion of resolution also. Now look at the maximas in the three. Rayleigh's criterion for two linear objects. The angular separation or the position of the first minimum d theta is lambda by a, which we have already done before. The minimum corresponds to the central maximum of the other. Hence, the angular separation between the two objects. Hence, for that instrument, limit of resolution d theta will be lambda by a. So obviously, for that instrument at a distance d from the object, we know that y will be d into d theta. But d theta is lambda by a. So y is equal to d into lambda by a. This is obviously equal to the first minimum from the center. Rayleigh's criterion for pair of point objects. Now we have a screen and the source. The rays of light should have passed through the circular aperture and we should have got a single bright point. But that does not happen. What happens is, what we see is a disk. Now that is the Aries rings, which makes the Aries disks, and the central bright band is here. The image of clip art here shows a real airy disk formed by passing a laser beam through 90 micrometer pinhole. The minimum separation between the image on the screen is a radius of the first dark ring. Now let's see the resolving power of a microscope. Obviously, we'll need a lens. So that's my lens AB, and we pass rays of light from the object. So this particular lens is called the objective. And the medium of refractive index N is surrounding the lens. So we have the object O, rays of light pass through the lens and it get converged at I. And we have, so O and O dash here are the 2-point objects separated by distance A in front of an objective AB. So we will have images I and I dash, and the angle is 2 alpha between them. So I and I dash are the centers of diffraction patterns, that the airy disk that we saw in the previous slide, and the rings due to O and O dash. So those are the patterns and the diffraction patterns, the maximas, as we can see. Point I is symmetric with respect to O. The paths AI and BI are equal. The actual path difference is O dash B minus O dash A. Now let's see it in details. So that's my earlier figure, and let's magnify this and see what is it. So we have O and O dash are the objects, rays of light coming out through them to the objective, that is to A, and that's to A, and that's to B, and this is also to B, and that's to P. And this particular, these are the two perpendiculars drawn over here, that is OC and OD. And this particular angle is alpha. So path difference is DO dash plus O dash C, which is equal to 2A sine alpha. For non-luminous objects, the solving power R is equal to 1 upon A, which is equal to 2n sine alpha by lambda. But we know n sine alpha is the numerical aperture. So that's 2Na by lambda, where n is the frequency, Na is the numerical aperture. For luminous objects, the solving power R is equal to 1 upon A, which is equal to 2n sine alpha, but now it is 1.22 lambda. That is numerical aperture upon 0.61 lambda. Now let's see the resolving power of telescope. Again, we have an objective here, but now the objects are at infinity, very large distance. Let us say d is the distance between the objective and the screen. We have OP, and these are the rays of light which are coming from infinity, hence it has to fall or meet at the focus. So we have this image I, and that's the pattern, diffraction pattern. Again, we have another object, and the image is I dash, and that's the dotted diffraction pattern. The angle is theta here, hence the angle here is also theta. So BI dash minus AI dash is almost equal to d into theta, which is 1.22 lambda. Resolving power R is equal to 1 upon theta, which is d upon 1.22 lambda. So that's the resolving power of telescope. Thank you.